All right, let's talk about math, but we're going to look at it in a completely different way. I want you to forget about the dusty formulas and all the rigid rules for just a minute. Instead, let's explore math as something we as humans actually created. A powerful, kind of beautiful language that we designed for one big purpose, to describe the universe around us.
You know, if you've ever sat in a classroom thinking, seriously, when am I ever going to use this? You are definitely not alone. I think we've all been there. But the answer is both simpler and way, way bigger than you might think. We use it every single day to describe pretty much everything. So yeah, let's dive into this.
So here's the big idea. Think of math not as this thing that was just out there waiting for us to discover it, but as a language that we invented. You know, just like English has its nouns, its verbs, and its grammar, so does math. And with that language, we can literally write the story of reality itself. To really get a feel for this language, we're going to build it from the ground up, piece by piece. We'll start with the basic nouns, then we'll move on to the verbs that connect everything. We'll see how we can just invent new words when we need them, learn how to describe change, and then finally put it all together to model the world. Okay, first things first. Every language needs nouns, right? Words for stuff. In the language of mathematics, our most basic nouns are called sets. This is the starting block for everything. The key phrase here is well-defined, and all that means is there's no confusion. For example, the rivers of India is a set. We know the Ganga is in, the Nile is out. No debate. But what about the 5 most renowned mathematicians? See, that's not a set, because renowned is totally subjective. It's not well-defined. And these examples just show you how versatile this idea is. A set can be a group of physical things, like a deck of cards. It can be a collection of abstract ideas, like the vowels, or it can even be a collection of other math concepts, like the numbers that happen to solve an equation. These are our nouns. So we've got our nouns, our sets. But a pile of nouns on its own is, let's be honest, kind of boring. We need action. We need verbs. We need rules that describe how the stuff in one set relates to the stuff in another. Now, here we need to make a really important distinction. A relation is pretty loose. It's any kind of link. For example, the letter B could relate to both Panu and Binoy. No big deal. But a function is a much stricter, more predictable rule. It's a special kind of verb that makes a promise. For every single input you give it, you will get one and only one output. If I plug 3 into y equals 2x, I'm always going to get 6. Every time, never 7, never negative 12, always 6. A great way to think about a function is like a simple machine. You drop something in one end, that's your input. The machine does its thing. It follows one specific rule, that's the process, and then it spits out exactly one thing on the other side, your output. It's this reliability, this predictability that makes functions the absolute workhorses of our mathematical language. So what happens when our language isn't good enough? What if we run into a problem we just don't have the words to describe? Well, just like we invent new words in English, like internet or selfie, mathematicians just invent new numbers and concepts. Here is a perfect example. For centuries, this question was a complete dead end. I mean, think about it. In the system of real numbers, all the numbers on a normal number line, this question has no answer. Why? Because if you square a positive number, you get a positive. And if you square a negative number, you also get a positive. So our language was literally incomplete. This quote from the amazing Indian mathematician Bhaskara really shows you just how impossible this problem seemed. For a really long time, this was it. The conversation just stopped right here. It was basically considered a nonsense question. But then mathematicians did something totally radical. They basically said, okay, what if we just make up a number to solve this? And just like that, I was born. It's not a number you can point to on the number line. It's a pure concept, a new word we defined by the very problem it was created to solve. I squared equals -1. And with that one single invention, a whole new dimension of numbers, the complex numbers, just opened right up. All right, so far, our language has been awesome for describing things that just kind of sit there. But reality isn't static, right? It's always moving, always changing. A car is accelerating, a population is growing. We needed a way to talk about motion and time, and that's where the grammar of calculus comes in. So check this out. Let's look at an object falling. Now, we can easily figure out its average speed over a period of time. Like between second 1 and second 2, we can see it traveled 14.7 meters, so its average speed was 14.7 meters per second. Easy enough. But what was its exact speed at the precise instant it hit the 2-second mark? That's a much, much trickier question.
But watch what happens as we make that time interval smaller and smaller. As we get closer and closer to that 2-second mark, the average velocity seems to be zeroing in on a specific number. From 1.5 to 2 seconds, it's 17.15. From 1.9 to 2 seconds, it's 19.11. You can see we're creeping up on a single value. We are approaching a limit.
And this right here is the absolute genius of calculus. The derivative is the tool, the word in our language, that lets us find that exact limit. It is the instantaneous rate of change. It's what lets us go from talking about your average trip speed to the exact number on your speedometer at one single moment in time.
Okay, we've got our nouns, sets, we have our verbs, functions, we even have our grammar for describing change, calculus. So now we can put it all together. We can start telling complex stories about the world, we can create mathematical models. Take population growth, for example. We can create functions where the input is time and the output is the size of the population. And the rates of change in those functions, their derivatives, well, those are just the birth rates and the death rates. This lets us describe and even make some pretty good predictions about how a population is going to change over time.
Or what about sports? The entire field of sports analytics is built on the simple foundations of sets and functions. It's what allows teams to model player performance, to analyze different strategies, and to figure out the probability of a certain play working. It gives them a real competitive edge.
Now for a classic, and I mean classic example. Back in the 18th century, the town of Königsberg had these 7 bridges that connected 2 islands and the riverbanks, and a famous puzzle popped up. Could you go for a walk that crossed every single one of those bridges, but only crossed each bridge one time? People tried it for years and years, but nobody could seem to do it. The great mathematician Leonhard Euler finally solved it, not by walking around the town, but by translating the problem into the language of math. He simplified reality. He modeled the pieces of land as simple dots, or notes, and the bridges as lines connecting them. By doing that, he turned a messy, real-world problem into a simple, clean network puzzle. And with that model, he proved that no, it was impossible. He didn't just solve a riddle, he basically invented a whole new branch of math we now call graph theory. So, you see, from the simplest idea of just grouping things into sets, to describing relationships with functions, to inventing new numbers when we need them, and finally, to capturing the very essence of change with calculus, we have built a language. A powerful language that gives us an amazing toolkit for making sense of the world.
And look, this language isn't just for mathematicians in ivory towers. It's for all of us. It's a way of thinking, a way of seeing the patterns and the connections where other people might just see chaos. So the real question is, what will you describe with it?